Okay, so I just went around and handed out this thing that says integration tables. Now this is an appendix in our textbook. You have them in the book, but I just didn't want to have to mess around with a book that weighs like 20 pounds. So these are the pages that appear. And they're just a bunch of integration formulas. So we've spent a lot of time, a bunch of time, this last chapter and previously, in earlier chapters, just when we're looking at integration, like making substitutions, learning different forms, is this a log form or a trig form, a power rule. But there are still lots of things we don't really know how to do yet. There's lots of, you could keep looking through chapter 8 of our textbook, where a bunch of our practice exercises come from, and you'll see there's like lots of other different techniques. A lot of that stuff we get to in Calc 2 if you're going to take that course. So this is just, we might, if you encounter an integral, out in the wild, and you're like, this isn't one of the forms that I learned, you can use these tables to help you out. So being able to use the tables just, relies on us being able to make the right substitutions, kind of recognizing the right form. And it's just a list of like 100 integral formulas. Sometimes it can feel like you're just digging through a big, finding a needle in a haystack. But they are organized by general type. So, for example, we start out with forms involving a plus bu. In these formulas, u is always the function, so that's going to be where your x's live, some expression with x's. A and b are always constants. So this is something that, you might be like, oh, that's like a linear, like 2 plus 3x. Sure. But u is just any function of x. So, 2 plus, x minus 5 squared could also be it, depending on what du is and whether or not we can make it fit that. But they do sort of arrange it by type, by general type. So we've got the a plus bu, we've got radical a plus bu, we've got forms that involve a sum or difference of squares. And we're just going to do a few examples together. Okay, so we've got x dx over the square root of 2 plus 3x. So this is like a linear, but it's a linear inside a radical. So I might try to look to see if they have some section that involves the square root of a plus bu. It looks like that section of formulas starts with number 16, though I don't think number 16 fits. How about 21? This one here. So u over the square root of a plus bu du. So in that case, if it were 21, so this one looks like minus 2a minus bu over 3b squared times the square root of a plus bu plus c. Okay. If it fits this form, what does u have to be? Yeah, okay, so here's something that's, I think, interesting, to me at least. This section, if we're using integration by tables, if we're using the table of integrals to help us out, this is really the only time ever where you're going to be like, let's let u equal x, right? Because when we make a general u substitution, letting u equal x doesn't change the way it looks at all, right? So it doesn't change the way the form appears to us, which defeats the purpose of making a u substitution. But that's not a concern for us when we're doing integration by tables, right? So if u is equal to x, then du is equal to dx. What's a? What's b? Yeah, so that seems to fit, and I don't even need to add in a constant to make our du work out. So let's see what we get. So negative 2 times 2 is 2 minus 3x over 3 times 3 squared times the square root of 2 plus 3x plus a constant. We'll clean this up a little bit. Not that there's a whole lot to do. And that's it. Now look, I know what you're thinking and feeling right now. I'm an empath. You're feeling kind of empty and hollow inside because you're like, what did we do anything? Like we didn't like integrate. What did we integrate? We used a formula. I get it. It's fine. We found an answer. It feels like we didn't accomplish much, you know? Like, I don't know. Doesn't it feel like unsatisfying?
You're really selling us.
Yeah, I don't care about this section. I cover it because it's in the outline that the college puts, you know, that the math department said we're going to cover integration by tables. Fine, I'm covering it.
It seems
all right.
like you care about it, you just need it.
Yeah. Oh, yeah. But those are my emotions. I do have a therapist, so don't worry. I'm working through it. But what's that? Yeah. Commiseration, right?
Almost there.
Okay, we can do it.
2 more.
We can do it. All right. Let's do another one.
Yay!
Yeah. Let's find a formula for this one. 24 seems pretty good. Let's see. So 24 says integral 1 over u squared minus a squared. So a difference of squares on the bottom, du equals. Oh, so first they just rewrote it as a different integral. I don't care about that. So at the end we get 1 over 2a ln absolute u minus a over u plus a. Okay, so if it fits this form, what is u?
X.
Yeah. So du is equal to dx. What is a? 2, right? Because a squared is 4. We have our du exactly, right? Okay, let's do it. So 1 over 2a is 1 over 2 times 2 ln absolute x minus 2 over x plus 2. So we get 1/4 ln absolute x minus 2 over x plus 2. Okay, that was a lot of hard work. One more. Interesting. We'll do this one more, and then I'm going to show you actually a fun way to do that one. All right, because I want to end on a high note. I refuse to let this be the way that we end this course.
This feels pretty great.
Okay, this one's a definite integral, so we'll use the table to find a formula that allows us to find the indefinite integral, and then we'll still have to plug in those limits. So we have a square root, we have a constant minus a function, or maybe a constant minus a function squared, something like that inside a radical up top. What do we think?
39. Yeah.
Look, you got, wow, that was fast. Hold on. Number 39 says integral absolute a squared minus u squared over u du equals
it's not out of you can take. I don't know right now. I put it 0
Oh,
on
we're
that,
almost there.
and I have it 92, and it's I get down to 60.
I'm already this is right to
Okay, does this fit? What needs to be what?
X is U.
Yeah?
3.
U is equal to X?
Yeah.
Okay. Then what's U squared?
What is B squared?
Hmm?
U is
2x.
Yeah, U is going to be 2X. So then du is 2 dx, and u squared is 4x squared. So that makes and you said a is 3. Okay. So then that makes the a squared minus u squared work out. We want 2x in the bottom, and that's actually easy enough to do. I'll just put in a factor of 2 here, which is really like a factor of a half. Normally we'd say let's put the reciprocal outside, so like adding a factor outside, but I'm going to put that right inside because I actually want that. That's my du. So now I think it fits nice. And what do we get? Anybody?
The square root of 9 minus 4x squared minus 3 ln absolute a plus the square root of, or a is 3, 9 minus 4x squared, all divided by 2x.
Great.
Those are our square brackets. Should be able to divide.
Mm-hmm. Good. All right. Let's plug in some limits. Oh man, it's gonna be fun. I'm having.
multiply by 1/2. Because there's one
So when we put in this 2 here,
multiplying by 2/2.
we were I mean essentially I just multiplied inside by 2/2. But when I put the 2 here, I was actually putting a 1/2 in here. So instead of putting its reciprocal, which is 2 outside, I put it inside so that we'd have the du. Does that make sense? Okay. All right, so if x is 1, then 9 minus 4 times 1, so that's root 5 minus 3 ln absolute 3 plus root 5 over 2 minus, if we put in a half, okay, 1/2 squared is 1/4, so that becomes 9 minus 1, that's root 8 minus 3 ln absolute 3 plus root 8 over 2 times a half is 1, okay.
How do you get a square root of 5?
So if x is 1, then
If x is 1, then that becomes 4, right? Oh no, you're right.
9 minus 4,
Yes,
yeah.
Yes, ma'am. I was thinking it was 5.
Mm-hmm.
Like not square root of 5. Sorry about
All right, so let's see, root 5 minus 3 ln, and then we have 3 plus root 5 over 2 inside the ln minus root 8. Oh. root 8 minus 3 ln 3 plus root 8. .8086 approximately. We did it. Yeah, good. Okay. Now, I'm not leaving it there. That's not going to define the end of our course. I would not ever let that happen to you. So this one that we did up here, dx over x squared minus 4. Look, the result ended up just being, we had the constant, but ln of some stuff, which kind of suggests that somehow we might be able to rewrite it in a way that lets us use like the ln form. So I'm going to show you a technique. If you want to just consume this for your entertainment, that's fine. It is something that we learn and do a bunch in Calc 2, and it's really kind of a neat algebraic technique. So we're going to redo this one. There's actually, I think, 2 other ways to do it, 2 fun ways to do it. I'm going to do the one that's like kind of purely algebraic. So it starts with, we're going to rewrite this function. I'm going to start with 1 over x squared minus 4. I'm going to factor that denominator. It's a difference of squares. And what I'm going to do now is find what we call the partial fraction decomposition, which just says, look, this fraction here is the result of adding 2 fractions together. Some constant that we don't know, I'll call it a over x minus 2, plus some other constant we don't know, b over x plus 2. Now this seems plausible that this could be the result of this, because if I had some constants over x minus 2, x plus 2, if I wanted to add these fractions, I'd have to get a common denominator. That denominator would be their product, right, because they don't share anything in common. So then we just want to figure out what those constants are. And if they are constants, then I could just integrate this by integrating that sum, and both of these would be a log form. So, so let's start with this equation. I'm rewriting it down here to give myself a little bit of space. And I'm going to rewrite this by clearing denominators in this equation, which, when we have an equation with fractions, that's a pretty common technique. So I'm going to multiply through by the LCD, which is just the product x minus 2, x plus 2. Okay. Here, everything cancels. Here the x minus 2's cancel. Here the x plus 2's cancel. So we have 1 equals a times x plus 2 plus b times x minus 2. I'm not multiplying everything out. I'm going to leave it just in that form right now. Whatever constants a and b are, they have to be such that this equation works out for all values of x, right? Like if these are just equal always, then these are equal always, meaning it works no matter what value of x you might choose to plug in. So there's a couple particularly convenient values of x we can plug in that'll help us figure out what a and b are. So let's consider this equation when x equals 2. If x is equal to 2, the left side is a constant, so the left side is still 1. And if x is equal to 2, then we have a times 2 plus 2, or a times 4, plus b times 0. So that cancels out. 1 is equal to 4a, so we get a is equal to 1/4. And if x is equal to negative 2, what's the equation that results? So what's b? Negative 1/4. Perfect. Okay. So now what we're going to do is throw these values up here. So the integral dx over x squared minus 4 is equal to the integral of 1/4 over x minus 2 plus negative 1/4 over x plus 2 dx. I'm going to split up the integral over addition. And while I do that, I'm going to yank these constants outside. So we've got 1/4 integral dx over x minus 2 minus 1/4 integral dx over x plus 2. Notice now each of these is a log rule because the derivative of x minus 2 is 1 dx, right? The derivative of x plus 2 is 1 dx. So we get 1/4 ln absolute x minus 2 minus 1/4 ln absolute x plus 2 plus a constant. If we go back to what we got in that example, I'm going to come right back to this page in a minute, but it looked a little bit different. But we could just do a little bit of algebra now and use properties of logs. So I'm going to factor out the 1/4. What can we do when we subtract logs? Divide inside, right? Like write it as a single log. So this is 1/4 ln absolute x minus 2 over x plus 2. Huzzah. There. See, we don't need the table for everything, you know. There's a big, there's a chunk of Calc 2 where you really just spend working on how do I integrate stuff that looks like this. Or, you know, an integration is all about trying to find ways to make your integral look different so that we could get to a point where we say, oh, I know how to do these now. You know, there's a lot of algebra in this case. There's another way to do this one, I think, where it involves like imposing, like rewriting it as like a trigonometric integral. So you start with something purely algebraic and you're like, if we make this substitution with a trig function, then it fits one of the basic forms that we know. Okay.